So this is a seminar. It's about security, how you can get started, and how you can get into security with something called a CTF, which is like a war game that you can play to exercise on like toy challenges and get the experience for security things. So this is our club. It's UofTCTF. What we do is we are a club that teaches workshops, that goes to conferences, security conferences. We also have war game events online that we play almost every single week. There's like a ton of challenges, a ton of opportunities to extend your skills, whether that is through certifications or formal training or courses or anything like that. CTF is just one aspect of it. So this is some of the stuff that we're going to be talking about. All of it is like categories of CTFs, which we'll get into what it is later. But anyways, the map of cybersecurity is massive. There is a lot of things that you can do. So like depending on your background, you can get into different aspects of security. Some of these are like kind of related to each other, but like physical security is about picking locks and like scanning codes like RFIDs and like cloning them. Hardware security is like glitching hardware to do things that like breaking them. There's like, this ties into robotics as well. There's like RFID security, which is intercepting radio frequencies, blockchain security, quantum cryptography. There's so much stuff. It is massive. If you have like any skills in any domain of IT, you can somewhat relate that. Like even biosecurity, that has a lot of usages as well. So like some conferences like DEF CON really emphasize this merging of different industries in cybersecurity, which is really awesome. But this is like a high level overview. What CTFs are is, let me talk about some of the things that you might be thinking of if you want to get into security. So if you want to get into security, security is really hard. The security landscape is always changing because technology is always changing, and it is relating to all aspects of technology. So how fast technology develops, security is developing 2 times as fast because you have the attackers and the defenders. So you're never going to be able to learn everything. And the stuff that you might want to know in security are also kind of gatekept by like a lot of knowledge, like networking, operating system, that is kind of crucial. But this is all stuff you can pick up through war games. It's really interesting though if you stick with it, because it makes sure that you get into the fields a lot deeper than you would have otherwise, because in order to exploit something, you need to know how it works at the fundamental level. Like a lot of vulnerabilities in open source projects are probably like you see a lot of these vulnerabilities in just bad implementations of like HTTP or like bad implementations of unzipping. So understanding like how the actual protocols work and being able to match them against the vulnerabilities or like see common attack vectors, that is something that makes you go more deep into the whole idea of computer science. It makes you a better programmer as well. So we'll talk about war games. War games are this way for you to gently be introduced into security. Essentially how it works is that there are a bunch of challenges that you play online, and they're like small challenges like go find a vulnerability in this website, find that some endpoint is not actually being checked for cookies. Maybe like they give you a file and you want to say like there's some hidden data in this file, where is it? So that is kind of like the challenges that you have. So that's like Jeopardy CTF, but there are like different aspects of security other than just like offensive security. So like there's King of the Hill, which is you set up an infrastructure and then someone else wants to try to pwn your infrastructure. So they want to take your infrastructure down, they want to reveal some secret that you're hiding in a database. There's also a boot to root, which is like you have access to a server, like you have access to this box online, you want to get in from boots, you want to get root access onto the server. So that is TryHackMe, does a lot of that stuff. So we're going to talk about Jeopardy CTF, and this is the CTF that has a lot of these toy challenges that get you into different types of security. So how it works is that you have the challenge, and there is a secret somewhere in the challenge, and you want to submit that secret to get points. And the reason why it's called Jeopardy is because there are different categories. So there is web exploitation, reverse engineering, binary exploitation, cryptography, forensics, open source intelligence, and then a multitude of other things as well. So we're going to get into web exploitation first. Some of the things that you have to know before doing web exploitation is how the HTTP protocol works. The basic idea is that any websites that you visit, you are going to communicate with them through the HTTP protocol, which is about sending requests and then receiving responses. So a HTTP request has this kind of structure where you have the request type, you have a multitude of headers which identify specifically what this request is going to be about. It includes things like the host, like the browser that they're using, or like the user agent, so the way that they're accessing this request, and a little bit about the context. And then there's the payload of the request, which has all of the body of the thing that you're going to be sending, that the web server is going to decode. When it does that, the web server returns an HTTP response. So it has a response type and a few headers and also the request body. So in this case, this is a forbidden page, but actually, I don't know why it's returning some HTML document. So that would be rendered in your browser as well. So it's your browser's responsibility to send requests and responses, but you can also manually send these with tools like curl. So this is how web server is defined. I'm thinking like most of you guys probably are building a web app, most likely have probably used web servers like Node.js or Flask, or setting up your own HTTP server. So like you are going to define endpoints, right? And endpoints have specific things that they return. They have specific status codes that they can return, and different request types, so like a GET request, a POST request for different purposes. So yeah, you might also be working with databases. So there's SQL, there's NoSQL. What we commonly, I guess, use in most cases is SQL because it's very scalable. So what you have is a selection of commands to interface with SQL, like selecting everything from a table, updating certain things in a table that match certain criteria, like if the person's name is Daniel and their ID is, or sorry, if the ID is 1, then you set their name equal to Daniel in the customer's table, or you delete a specific row in a table as well. So that's about SQL. There is a specific attack you can do with SQL that you might have heard of before, which is SQL injection. The idea is that if, for example, you have some endpoint that is going to append some user input to like a SQL query, what you can do is the user can send in an input that is going to remove the condition that it was possibly going to be appended to, because like the only reason you would want to append something is if you want a condition. So this is going to bypass the condition, because what it's going to say is that the condition beforehand, or 1 equals 1, which is always going to be true. And then it's going to comment out the thing to the right of it, which is like something else that is going to be wrapping around the user input. So that's an example of attack. What you can do with this is you could possibly leak all of the information from a table, or you could even delete things from a table given certain circumstances as well, depending on the request. There is another vulnerability that you might have heard of, which is cross-site scripting, and there are two types. So the first type is a reflected cross-site scripting attack, which is essentially you are sending this request that has been crafted specifically with evil malintentions. So maybe what it's doing is it is sending your cookies to like a different server. That's what the request is doing, and then you get a evil response back. So maybe like an evil request is also like sending your money to an attacker, or like deleting your accounts. So like the idea behind this is that the attacker will give you like a URL to click on, and then once you click on it, you get logged into Facebook, and then this request also contains something that is also going to delete your Facebook account as well. So that's the idea of XSS, that you have to be phished. There is also persistent or stored XSS that is going to be something that an attacker uploads to the server. So like, for example, like a comment section, they upload some like JavaScript script, and for some reason the server would render and like execute that JavaScript script, so they can do anything. So anyone else that visits the website would render that comment, and then that comment also has the JavaScript script that is like defaultly executed by like an iframe or something like that. So anyone that visits the website is going to have that script run on your computer. And the idea is that it's stored somewhere in a web server. Okay. Another attack is a directory traversal. So depending on how you set up your web server, you can be able to use like these backtick commands that is common in like Unix file systems to go back a directory, and you can like enumerate through a bunch of files. You can go back to like the root directory and then read like certain things like the etc password file, which has like a list of all the users. So that is like an example of an attack that you can do. Go to like, I guess if you have like some endpoint that has allowing you to like look through images on a web server, you can do this attack and go to like the root directory and then just find some other files on your system. And maybe I'll skip this one because, okay, I'll briefly explain this one. If you're like familiar with Flask or Jinja, Jinja is like a templating engine. So the way that websites can be rendered is like obviously it can be like HTML, but sometimes you want to include like Python code as well. So Jinja allows you to like execute specific Python that is going to be later compiled into the HTML for your site. When this happens, what the attacker can actually do is they can, for example, like a user can change their bio on their profile. Well, if the user does like os.system ls exec password, well, that is interpreted as Python commands. And what that's going to do is it's going to actually this should be cat etc password. You can't list this directly, but anyways, this would just run this system command anyways. Maybe I'll skip this one. So the basic idea with web exploitation, the fundamental thing that you want to know is that recon is the most valuable thing. And the reason why that is because web technologies are very vast. Like there's so many frameworks, there's so many servers that you're using, and they're all structured in different ways. So like there's certain files that a framework uses. For example, PHP will use certain endpoint routes. Most sites have these files like robots.txt or like a login endpoint. Sometimes they have a sitemap XML that allows you to show all of the other routes that are on the site. And you can also see specific things like the web server. So like if they're using Node.js or Nginx or any other web server, you can look through the vulnerabilities if there is any vulnerabilities on a specific version. So recon is like the main thing that you want to do in web exploitation. After you do that, you just collect as much data as you can, whether it be a cookie. If it's a cookie, you can try to crack the cookie. If it's encoded values, see if you can decode it in any sort of way. And you can test common attacks. So there is like a multitude of attacks. So there's something called hack tricks, which is like a book of a bunch of payloads that you can do to just see if something is vulnerable. So like SQL injection, there are like a bunch of payloads that you can test out on like an input form. And essentially you are just like a script kiddie, you're trying things out. But it's important because, well, this is the low-hanging fruit and you want to see if there is any sort of gap in the system in that direction. Okay, so we'll talk about reverse engineering now. The basic idea with reverse engineering is that there are pieces of software that you don't understand. They're hard to understand how they're built, right? You have like a C compiler and that compiles C code. How do I find out it's like the original program, the C code that it is? Because when I have the code, it's an executable. So there are different things that you can reverse engineer. There is PE, ELF, Android apps, like arbitrary programming languages, virtual machines, hardware, so on and so forth. Actually, before I continue, are there any questions on any of the stuff so far? You can like do a thumbs up if everything is fine. If you have any questions, just raise your hand up. But yeah, so that's the idea of reverse engineering. So we'll talk about a few things that you might want to know when reverse engineering. The main important one is a file format. So executables have different formats, right? For Windows, there is a PE format, and for ELF, for Linux, there is the ELF format. So I'm going to talk about the ELF format. If you want to see the actual file format, you can use the file command on Linux. You can see that this is data, this is a P executable, this is an ELF executable. So the ELF file format is structured in such a way that there is some text, which is like the assembly that's going to be written. There's some data that has the like constant data or like variables, like global variables that are going to be added later on. There are also some like metadata, like ELF type, stuff like that, like versions for the operating system to assist in actually loading the program into memory. And there's also segments. So there are like different segments that are used to help load the program into memory. Actually, a lot of this is for the operating system. But if you're reverse engineering, some of the main things that you're going to be looking at are the text section, the data section, and how big some of the sections are. So I guess if you have actually worked at like a hardware level or like a low level, you understand the idea of a machine code. How it is that you are mapping essentially a stream of bits into the hardware. So like some certain parts of some segment of the machine code is relating to what sort of register that we're using, and then sometimes you can like move in immediate values. If you haven't taken a course on any like assembly or like computer architecture or organization or anything like that, then it would be kind of hard to understand, but just understand that it maps somewhere to the hardware. So assembly is the human readable version of the source code of the machine code. And this is kind of how it looks like. This is machine code in hex. We don't want to represent it in binary because that's going to be too large. But there is the x86 assembly, which is the human readable version, the mnemonic. That's what they call it, the mnemonic. So yeah. So commonly in the CPU, the way that we actually run things is we use registers. So these are like small storage units that are like very fast to write to, very fast to read from, because they are directly inside the CPU. So like at a hardware level, there's RAM, and there's also SRAM, and SRAM is more expensive. DRAM is like the stuff that you use in like your RAM sticks, but SRAM is more expensive, and that is what CPU registers are made of. So we'll go for an example of how assembly is executed. Essentially, we have this program here that has some assembly move EAX free. So what this is saying is that we have the EAX register, and we're going to move the value free into it. So I have the registers down here. EIP is like the instruction pointer. So right now it's 0x8049000. EAX is the value free. So if you go to the next instruction, what this says is that we're moving the value 4 into EBX. So you can kind of guess what's going to happen to EBX. It's going to have the value of 4 now. The last one is we're going to add EAX and EBX. So what this does is it is taking the value of EAX and the value of EBX, and it's going to add them, and then it's going to move it into the value of EAX. So EAX is the source that you're going to put the stuff in. Okay, so that's an example of assembly executed. How do we actually create the assembly, right? We have the source code, but that is not directly assembly. So this is like a high-level overview. If you're interested in how compilers actually work, I'm going to be hosting a compiler workshop at 5 p.m. so you can actually understand how this stuff is actually converted to assembly. It's really interesting, but it's also really complex. But it's also kind of elegant. But the basic idea is that you have the source code. You convert it into a smaller intermediate representation. You convert that intermediate representation into assembly, and then you have something to convert the assembly into machine code. And all of these processes are using different programs, essentially. So disassembling is what we commonly do in reverse engineering, right? Because when we have a program, all we have is the machine code. So we want to convert it to assembly. And then after we convert it to assembly, we want to convert it into a high-level intermediate representation or source code, right? If possible, if it's like a very easily revertible assembly, then you can convert it back into something like source code. So this is like Java. Java has their bytecode, which is very simple. And sometimes when you open VS Code, you open like the class object, and you can actually see the Java original source code, because it's very easy to decompile that. So there's common decompilers, there's Ghidra, there's Binary Ninja, there is IDA. The one that you pick does kind of matter because they have different ways to actually use it. Ghidra is free, obviously, but Binary Ninja and Hextrace are more powerful. So debugging is also really important, because when you're actually like looking at the decompilation of things, it is not really understandable. Like maybe I can find an image of decompilation compiled driver. Like decompiled code is not readable. Like it's meant to be readable, but it's also not really good to read. And also like the whole way that it looks is okay. So I guess this is like an example, or this is actually assembly. This is like this is something. I guess this is like, okay, so this is like a decompiled code. So like you had a program and then you decompiled it. What really is happening here, right? Well, I say there's like a while loop, there's like an if statement, but it gets really long. Like for here example, there's like report range check failure. What does this command mean? Debug break. Like I could read into like what all of these functions mean, but sometimes it's just faster to execute the program at a certain point and then see what the results actually are doing. So that is what debugging is doing. Debugging is running the program at a specific point, and then you can go through the next line and then manually see the outputs of the functions. So for Linux, you have GDB, and for Windows, you have x64 debug. Okay, so the basic idea with reverse engineering, this is the philosophy, I guess, is that you want to know as much as you can about a program before actually going into debugging, because debugging is expensive, it's time consuming. So you want to do some metadata analysis. You want to see specifically like some files to say that maybe this program is compiled by Python. Like Python executables commonly have the string. It's like compiled with Py executable creator. I forgot like the name, Python pack or something like that. Or like if it has been like packed, which is like something to obfuscate the program, then it could be say like packed by Famida, something like that. So after you do that, you can run the program in a sandbox if it's malware, or if it's on like something that you can't run on like Mac OS and you're like on a Windows computer, you have to use an emulator. You can disassemble, decompile, and then when you decompile, it's going to be messy, so you need to clean that up, sort of, and then do debugging. So you do debugging if you have like certain parts that are not really understandable. You have your disassembly at the side, but then the debugger on the other side to kind of cross-reference, and that's how you understand a program, right? It's a very messy process, but these are the best tools that we have, and you'll start to find patterns. Like this stuff is very hard to understand. Some of the symbols are kind of blurry and like obfuscated, but if it's a pattern, right? Everything has a meaning. If you do enough times, you start to see the patterns anyways. Okay, the next level of reverse engineering is binary exploitation. So once we understand a program, what if we can exploit it? What if we can make it do whatever we want it to do? So there are things that are different when you actually load a program into memory. So you have a program on the disk, right? And obviously it has like information about it, like the actual assembly, the header information, stuff like that. When you load it into memory, you get a stack and a heap. So like you get the same things on the disk, but you also get a stack and a heap, and then some information that the kernel needs to actually execute it. So the stack and the heap can be exploited because depending on what the user does, some things like the user input are going to be stored on the stack, and some are going to be stored on the heap. So yeah, so this is kind of what you have. You have a new stack and a new heap whenever you execute a program. So the stack is what we're going to be talking about. There is heap exploitation, but stack overflows are like the most common way that you exploit a program. It's like the thing that everyone gets introduced to in binary exploitation. So the idea of a stack overflow. Now, what does the stack actually do? The stack is not the data structure, so you probably learn about the stack with the push and a pop in like some theoretical algorithms class. The stack is used in a program to actually manage which functions to jump to. So if you're in a current function, the stack manages all of the local variables in the function and also what function to return to. So that's the idea of what a stack is. And a stack is outlined by two registers. So there's the stack pointer register and the stack base pointer register. And obviously, this is like a subset of the stack. So like the entire stack is like 4 megabytes, but we only care about certain segments that are related to the program, because like we're not going to have 4 megabytes for an entire program. So we're going to take like 2 pointers and then say like everything between the 2 pointers is the current function. So that's what a stack frame is essentially. So how function is called is you have some arguments, obviously. So the arguments are going to be pushed onto the stack. And then you have the function body, which manipulates both registers and stack. And then you have the epilogue, which is the important part. So what you're going to do is you're going to clean up the stack. So the space between RSP and RBP is going to become 0. And then what you're going to do is you're going to take the topmost element of the stack, which is what RSP points to. And that's the address of where you return to. So we can actually exploit the address that it returns to. If, for example, we have a program that has our input buffer here, and our input buffer is going to be stored on the stack, and like this is like this is the return address, and like there's some other local variables that are given as arguments to the program. We have our input buffer here, so what we can do is we can write a very long input. And this is going to overwrite the return address. So now when a program returns, it's going to return to 0x41414141. And what we could do is we could actually change this to some address that we actually want. So this is the idea of stack smashing. This is how you make a program do what you want. And a specific usage of this is return-oriented programming. So there are certain restrictions on what you can actually direct a program to do, but certain things in a program are trusted by default. And this is code that is present within functions that are linked within the program. So you find specific snippets that are like small pieces of code that have a return before it. And what you do is you push the address of this code onto the stack. So when the stack finishes, it returns to this segment of code, and then it returns from that segment of code to the next segment. And you can make the program do larger operations of actions, essentially. So that's the idea of return-oriented programming. And we'll talk about it more in the compiler workshop if you're interested as well. So if you want to find gadgets or tools, you can download them off the internet as well. I'm not going to talk about format strings, not really relevant. The philosophy of binary exploitation is that you have like a fixed amount of size to work with, like the stack has like a fixed amount of size, the heap has a fixed amount of size, but you also have like things that you can do like arbitrary write, arbitrary read. You saw the ROP example that we are like combining a bunch of snippets to do larger things. The idea behind binary exploitation is that you want to find these small like arbitrary like specific writes or like reads, and you want to combine them together to make larger programs. It's kind of like programming in that sense, but your actual things that you can program with are very limited. I'll just do a quick check on time, I guess. Okay, we have 7 minutes. Maybe it'll go on to like 10 minutes afterwards. But yeah, I'll try to go a little bit faster. There is forensics. So forensics is the entire process of finding hidden information within data. It's like if a file is deleted, it's not actually deleted. This is something that is used later on, but every single file has metadata. So metadata has, date, comments, file type, and some comments as well. Specifically with images and videos, you have something called an EXIF metadata. So if you take like a picture on like your phone or like an Android phone or iPhone, it stores like the phone that you use, the camera, the location sometimes, the date that it was taken at, and you can find this hidden data by looking at the EXIF metadata. So what Facebook and like other sites do is they remove the EXIF metadata, but if you were to just like send the photo that you have in your phone, then that data is remaining there. So that's something that you can do with metadata. What you can also do is you can hide certain information within other data formats. So let's say, for example, you want to send a secret message to your friend, and you want to send it for like an obscure data formats that nobody will check. Like maybe store your passwords in like an image, but you don't want people to open the image and just find your passwords. So this is like the whole process. You have data that you are encoding in like a different format. So a classic example is LSB, which is a least significant bit. So like how PNG or like bitmap is created is that you have like a little bit of metadata at the top, and then you have the actual RGB values. Well, RGB, if you like know binary, you have like you can convert RGB into like binary, and then binary has like the final bit, like the least significant bit. So what you can do is you can change that to the message that you want. So like if I have the message 010, I go to like the pixels of the image, I change the first one to 0, and then the second pixel has like the final bit is 1, the third bit is the final bit is 0, and then the color is like pretty much the same, right? Because you're just changing it by like one bit. So the color is pretty much the same. The image, like here, original image, is very similar to the final image. The colors are pretty much the same, but the final bit of every single pixel is different. And then you can read the final bit of the image to encode a message, essentially. There's also spectrograms, so like audio waveforms. You can have like different hidden information inside the audio waveform as well. Right? You can also like put files on other files. So this is kind of cool. So I have like a JPEG image, and I can put like a secret.txt file inside the JPEG image. How this works is that the file formats, how like the libraries actually parse it, is very predictable, and you can put things in like the end of a file, which like the file parser doesn't actually care about, and you can like put this txt file in like the end of a JPEG image. So yeah, so if you are curious on like how you can actually find this stuff out, find the hidden information, there's a site called the Parasolve. You just upload an image or like file, any file. It like runs through a lot of operations, like looks at the strings, looks at the metadata, looks at like embedded data inside of that. So Parasolve is really powerful. There's network forensics, which is like you are able to listen to network traffic. So like your computer is going to have inbound traffic and also outbound traffic, so you can capture that, and you can keep that and replay it and like look at what your computer talked to you. And what you can do is you can like use some network analyzers to find specific sites that you've been talking to, specific protocols, files being sent back and forth around. This is some cool things that you can do with that. There's also memory forensics. So like every single program, every single thing that you're executing is going to be in a RAM at some point. And when you shut your PC down, the RAM is cleared later on, but you can take like a snapshot of the RAM, and you can see what processes the person is running if you have like a snapshot of the RAM. So you use a tool called volatility to look into that. Disk image forensics. So let's say you like have a copy of your disk. You can look at like how the files are written to the disk. And like the idea is that like files, if you've ever like deleted a file and like you want to bring it back, well, it's not actually deleted. You can like do Control-Z to bring it back. And also like even if you like permanently delete on Windows, it's not actually deleted because the actual underlying file system didn't actually delete anything in that. So you can use disk image forensics to parse through like a disk image copy and see what sort of files there was on there. So forensics is probably like the hardest category because there is not really a good way to go about it. Like for like web exploitation, there's like recon. You spend a lot of time doing recon. For reverse engineering, it's literally just this is the assembly. There's no more things. Like you don't have any wildcards. Just read the assembly, decompile it, try to figure things out. For forensics, you kind of have to piece together a timeline. So like usually it's used in a digital response, like incident response, like your company had a cyber breach. This is all that we have. You have to work with what you have. And sometimes you have to piece together a timeline between these disparate pieces of information. Yeah. Okay. So cryptography might be kind of, I don't know if anyone here is like really interested in math. This part is a little bit technical. The basic idea is we want to establish three goals. So it's the math behind security. We want to establish confidentiality, which is our messages should not be able to be readable by anyone that has it. We want to establish integrity, which is like, I want to ensure that my message hasn't been tampered with. And we want to ensure authenticity, which is saying that I want to ensure that the person I'm communicating with is the person that I should be communicating with. So these are three goals. How it does that is with a variety of different things. So there's encodings, which are like ways to change some data format into another. So you probably know ASCII, UTF-8. There's also base64. So base64 kind of looks like this. If you have like the number 0, that goes to A. If you number 63, that goes to this. So it's like a dictionary or like a hash map or something like that. You also have ciphers. Ciphers are this idea of turning your plain text into ciphertext and also decrypting that ciphertext back into plain text. So you can encrypt something and also decrypt something at the same time. And it requires something called a key. So a key is something that you feed into a cipher plus the plain text. So plain text plus key into the cipher, and you get the ciphertext. So there are two types. There is a symmetric cipher, which has the same key to encrypt and decrypt, and also an asymmetric cipher, which has two keys, one for encryption, one for decryption, for different purposes. All right, so we'll talk about an example cipher. This is a one-time pad. It's very simple. What you do is you have your original message and then you XOR it with your key. So your key is the same size as the message. You can like copy the key several times to make it the same size or like reduce the key a little bit to make it the same size. But essentially, once you have the key, you XOR it with your message and you get something else. And the property of XOR is that if you XOR the same thing twice, you get the original message back. So this is something that you can decrypt. You just XOR it again, and that is how you decrypt the message. AES is like a very secure way to actually encrypt things. So how it works is that you have a key of a fixed size, so it has to be fixed size, and a fixed size plaintext. And you can encrypt and decrypt with these fixed size plaintext. The way that AES is actually implemented is very convoluted. It's not really worth mentioning. It's not a matrix operations. It's not really worth mentioning here, but it's definitely understandable if you spend enough time with it. AES only works with a fixed size input, obviously. So if you have like a larger input or a smaller input, what you have to do is you have to split the plaintext up into 128 byte chunks, because that is the input to AES, 128 bits. If you want to encrypt something larger, you have to split it up into 128 bit plaintext chunks, essentially. So this is how you encrypt a larger message. There is an issue with the system to encrypt a larger message, and that is structural properties remain. So like this is the original image, this is it encrypted with ECB. You can still make out the details of the penguin, like the structural information remains. It's an isomorphism. So because it's like one-to-one. But you have an encrypted using other modes that cause more noise and diffusion, and you just can't make out that this is a penguin originally. So that's a problem with ECB that you might see sometimes if you use it. There's the DLP problem, which is this problem. It inspires something called RSA, which is a symmetric cipher. Essentially, you have given primes, and you compute this message, which is detotient, and you find a public key which satisfies this relationship, and a private key which satisfies this relationship. And what you have is, what you can do with the properties of these primes is that E times D are modular inverses. So what you can do is if you encrypt something, so you take a message, raise it to the power of E, and then you do a modulus with N, you get the ciphertext. But because D and E are modular inverses, you can take your ciphertext, raise it to the power of D, and then mod that, and then that's your message. So asymmetric cryptography, if you remember what that is, you have a public key and a private key, so two keys. One key for encrypting, one key for decrypting. E is your encryption key, D is your decryption key. So that's the basic idea there. Okay, so here's an attack against RSA. Maybe I'll just skim over this. Essentially, pretty much, you have two messages with different keys. But like the thing is, even if you have different keys, you can do something that allows you to recover the initial message. So if you have like the same modulus, which is here, even if you have different keys, you can use Bezos identity to find the original message. All right, so the basic idea of cryptography is that it is math, and in math, there's like a heavy emphasis on formal proofs. Cryptography doesn't really have that. So not a lot of things are actually proven in cryptography. The only thing that is actually truly proven to be secure is the one-time pad. So a lot of things are assumed to be secure because of so-called hard problems. So RSA is based off the hard problem called the discrete logarithm problem. There's also specific things that are based off like elliptic curves and like lattices and stuff like that. But cryptography is all about breaks. So like we have these supposed notions, and there's a specific time to actually brute force and break it. If you find a break, all that is saying is that you found a way that is more efficient than brute force to break the algorithm. So it's all about finding breaks and designing algorithms based off what you can prove to be secure. And if you can't prove it to be secure, you find a problem that is really hard and computationally expensive to break. Okay, OSINT. So this is one of the last things we're going to be talking about. Open source intelligence, essentially stalking people. You can use the internet to find information about people. So you can find social media accounts, emails, numbers, marketplace accounts, IP addresses, crypto wallets, locations. A bunch of stuff should not be on the internet, but it is on the internet, and you can use that to your advantage. So if you've ever heard of Google dorking before, essentially it's a specific way to search Google to match specific things. Like you can say that I want only results from google.com. I want only files that are like PDFs. I want only results that include the specific keyword in my text. So like something that you can do is you can go like search confidential and then say type PDF, and you can find PDFs that have the word confidential in them. And like if you search enough, you can find like possibly trade secrets or like confidential information just using google.com. Yeah, what you can also do is you can use tools that help you find usernames across the internet. So this is something called Sherlock. Essentially what it does is it goes on like a website, and it goes to the forget my password thing. And what it does is it like requests your username. So like you request a username, and if you have like or like it even goes to like mysite.com/users/username, and like you see if you get like either a 400 like not found error or like 200. If there's a 200, then there is a user. So like that's essentially what it's doing. You can find users by just looking and exploiting things on a website. There's also like GitHub repositories. They have like emails here, and also like GitHub can reveal potentially secrets if you don't sanitize your repository. So like maybe if you're going to submit something to actually check if you leaked an API key or something like that, you can run TruffleHog to find if you actually leaked an API key. Yeah, location search. If you're using Google Maps or like if you have an image of something, you can use Google Maps or OpenStreetMaps to see if it actually matches. There's what3words, which is like a way to describe locations. There's also reverse image search. You have an image, you can try to find a location. This thing called Yandex reverse image, it's the Russian search engine. It's really good. It's really good at this type of stuff. So the Russians have really good technology. There's also domain groping, which is like you are looking for like DNS records on your domain. You're looking for like subdomains, and you can find like things like IP addresses, like DNS records, and it kind of generates a map. So this is called bbot, and this is kind of what it does. And you can also use archival tools like Internet Archive, archive.today, to go on like websites that like previously had information on them. Maybe it's like removed right now, but you can go on the Internet Archive and see if there's anything relating to that as well. And the basic idea is that you just have a bunch of tools, try what you can. It's kind of like a shotgun approach, try what you can. There are like actually ways to go around it. Like, so if you're like accustomed with the actual culture of, let's say, this area, like there's like location, if you're like knowledgeable about the culture of that area, or like just recognize the location, like you do a lot of Google Street View stuff, that helps a lot. But sometimes it is just about using our tools. Sometimes it's about intuition and understanding some of the context behind the sites, like phone number sites, job search sites, or like location image data, essentially. Okay. So there's like a few other things that you can kind of see during CTFs. Other challenges is like there's AI challenges, prompt injection challenges, make an AI do what you want. So you can use a bunch of prompt injection attacks. We have like a workshop on this previously if you're interested in prompt injection. There's like attacks or like, there's like challenges which are like coding. So if you do a lot of ICPC or like professional coding, there's like coding competitions as well. You want to achieve like very low time during these. There's like there's challenges where you like write in isolangs, and there's also like blockchain exploitation. And the cool thing about blockchain is like once you exploit it, you can take all the money that is in that blockchain as well. So yeah, so that is pretty much all that we had to talk about. Hopefully you learned something cool. There's more stuff at our site, but yeah, that's pretty much it. Hope you got interested in CTFs